So today we're gonna do the tutorial. I'm gonna take you through the tutorial sheet. So let me show you. Let me show you the tutorial sheet. You probably know which one it is. So if you go to week 5, this is week 5, right? So the tutorial sheet is this one here. So this is on R clearly. So as usual, I will take you through each command or each line, and also at the end, if I have time, I will do the exercise. There are 5 exercises at the end. I will do as many of them as I can depending on the time. Okay, guys. So let's begin. So the first thing you need to do is to open R. So what you do is you go into this start menu. It might be different on a Mac, I don't know, but I'm using a PC. So you go into and choose R, and out of these two, you choose the 64 version. So this is what you will get, right? All right, guys. So I'm going to take you through the different commands, right? But before I do that, let me show you the first page. The first page of the tutorial sheet contains this table, right? R has many distributions. Nearly all the distributions that you will encounter in your lifetime are contained in R. Some of the discrete distributions contained in R are the binomial, Poisson, geometric, and negative binomial. And some of the continuous distributions are the uniform, normal, exponential, gamma, chi-square, beta, and student's t. Now, R has certain abbreviations for this distribution. So for binomial, is abbreviated by BIN-OM. Poisson is POIS. Geometric is GOM. Uniform is UNIF. Normal is norm, and so on. Now, suppose you want to compute the density or the probability, the CDF or the quantile function, or generate random numbers from a distribution. These are the syntax. So these are the syntax for any distribution. If you want to compute the density or the PMF, you use the D and the name of the distribution. If you want to compute the CDF, then you use P and the name of the distribution. And if you want to compute the quantile, then you use Q and the name of the distribution. And if you want to generate random numbers from a given distribution, you say R and then the name of the distribution, right? So these 4, the D, P, Q, and R, computes the density, probabilities, or the CDF, quantiles, and random numbers for any given distribution, right? So for example, if you want it for the normal, the D norm will compute the density of the normal, P norm will compute the CDF of the normal, Q norm will compute the quantile of the normal, and R norm will compute the random numbers from a normal distribution, right? So let's go to the next page. The next page, that is page 2 of the tutorial sheet. As usual, if you have questions, guys, just use the chat room, okay? All right, the first thing I'm going to do is I'm going to plot the density of a binomial distribution. So this is what you will do. First, you need to define where you want the density from, all right? So 0, 50, 1. So it will generate these numbers 0 to 50 in steps of 1, right? And then you want to compute the density of the binomial distribution, which is the PMF, right? Remember that the binomial distribution has two parameters, the size parameter and the probability parameter. So let's take them to be 50 and 0.6 respectively, right? Okay, so this is what you will get, and if you plot xb versus pxb, this is what you will get, right? You see? So this is the probability mass function of a binomial distribution versus x. If you like, you can join them up using, so if you say type equal to L, it will join the points together, and you get this nice looking probability mass function for a binomial with parameters 50 and 0.6, right? Now, suppose you want to compute the PMF of a binomial distribution, say at 35, right? This is the probability. So what I have computed is the probability that x equal to 5 when x is binomial with parameters 50 and 0.6. So that's what I have just done, right? Now, suppose you want to find the probability. Okay, suppose you want to find the probability that x less than or equal to 25, right? When x is binomial with parameters 50 and 0.6. In this case,
I'm sorry, and we can only see the PDF and we can't see what you are typing.
sorry. Okay. Sorry. What am I doing? Did I? Share screen. I must be doing. Can you see it now, guys? Hello? Hello, guys. Can you see it now or no?
Yes, we can. Yeah.
Okay, thank you. All right, I'm sorry. I'm sorry for. Let me continue. So what I was doing so far is that I was in this part. I did a plot of the PMF of the binomial distribution using these three commands, right? Using these three commands, I showed you how to draw a plot of the PMF of a binomial with parameters 50 and 0.6. And this command here computes the PMF of a binomial with these parameters at x equal to 35, not 5. I think I made a mistake. It should have been 35, not 5. Now, suppose you want to compute for the same random variable. Suppose you want to find the probability that x is less than or equal to 25. Then you will just say, so this command here, the one I just typed in, right, is the probability that x is less than or equal to 25 when x is binomial with parameters 50 and 0.6, right? Okay, now suppose you want to find the probability that x is between 20 and 30. Right, in order to compute this, first you need to compute the probability that x is less than or equal to 30, right? And take away from that the probability that x is less than or equal to 29. Do you see why it is 29 and not 29? I mean 19. Do you see why it is 19 and not 20? Because this probability here, you can write it as the difference of the probabilities that you can write it as the difference of these two probabilities. All right, so in order to compute this probability, you need to compute the probability that x is less than or equal to 30, and take away from that the probability that x is less than or equal to 19. So the answer is 0.5521499, right? Okay, and similarly, if you want to, suppose you want to find the quantile function of the binomial distribution, then you will use the qbinom command, qbinom. So for example, the median of the binomial distribution with parameters 50 and 0.6 is 30, right? And the first quartile is 28. The third quartile is 32, and so on, right? Okay, the next thing is to generate random numbers. Suppose you want to generate random numbers from a binomial distribution with parameters 50 and 0.6. And here you have 5 numbers. 5 here denotes the number of random values that you want to generate from a binomial distribution. So these are 5 random numbers from a binomial distribution with parameters 50 and 0.6. Okay. All right. So far we talked about the binomial. Now let's talk about a continuous distribution. I mean, binomial is a discrete, as you know, it's a discrete distribution. Right. For a continuous distribution, let's take the normal distribution, which is the most common continuous distribution. So for example, denorm, the command denorm will compute the density of the normal distribution at x equal to 0, right? So this is the denorm computes the PDF of the standard normal distribution at x equal to 0, right? Okay, now if you want to find it, if you want to compute the density at different values, like say you can use this. So this command here computes the density of a normal distribution with mean equal to 4, standard deviation equal to 10. So it computes the PDF with mean equal to 4 and variance equal to 10 to the power 2, right? So that's what you get, right? So mean specify the mean parameter of the normal distribution, and ST specifies the standard deviation. In other words, the square root of the variance, right? Okay, and similarly, just like in the binomial case, you can plot the density of the normal distribution using the plot command. So let me show you. So let xn to be a sequence of these numbers from -26 to 34, and let yn be the values of the density at xn with mean equal to 4 and standard deviation equal to 10. Then if you say plot xn comma yn type equal to L for line, this is what you will get, right? Excuse me. Let me close this email. Right, this is, so you see here that what you see here is that the density of a normal distribution with mean equal to 4 and standard deviation equal to 10, right? Okay, guys, right. All right, next thing. Now, how do you compute the probabilities associated with the normal distribution? To do that, you use the command pnorm. Right? So suppose you want to find the probability that x is less than equal to 4 when x is normal with parameters say 4 and 10 squared. Now to work this probability, you use the command pnorm for mean equal to 4, st equal to 10, and that will give you 0.5 as it should, right? So this command here will compute the probability that the variable x is less than equal to 4 when the normal variable has mean 4 and variance 10 squared, right? And you can also do this, right? In this case, you are computing the probability x less than equal to 4, less than equal to 8, and less than equal to 12, right? Okay. And you can also use the qnorm command. The qnorm command can be used to compute the percentiles of a normal distribution. So for example, q at the quantile at 0.975 is this, right? And the quantile at, so whenever I don't put mean or ST, that means I'm using standard normal. So in this case, automatically mean is 0 and ST is 1. Now, if you want to specify the mean and ST, you have to give these options mean and ST. So in this case, the quantile at 0.975 is this, right? And the quantile at 0.5 is 4, as it should, right? Remember, 0.5 is the median or the mean. For the normal distribution, the mean and the median are equal, right? So it should be 4, right? And you can also use the rnorm command. So suppose you want to generate random numbers from a normal distribution. So suppose you want to generate 5 random numbers with mean equal to 4 and st equal to 10. And this is what you will get. So these 5 numbers are coming from a normal distribution with mean 4 and standard deviation 10, right? All right, next thing, I'm going to show you how to draw a PDF on top of a histogram. Right? This is important because this is relevant to the coursework that you will need to do. Remember, there's an ARC coursework which is due sometimes in April. You need to look up the website, right? So for this, the first thing I'm going to do is I'm going to simulate a random number of size 10. It's a random sample of size 10 from a gamma distribution with shape parameter 200 and scale parameter 2. Remember, if you did, I'm sure you did probability 1, right? The gamma distribution has 2 parameters, shape and scale, right? Okay. So now what I'm going to do is I'm going to do a histogram of the data, of the simulated data, right? With frequency equal to false. And let's take the limit of the x-axis to range from 280 to 500. So this is what you get, right? So this is a histogram of the data that we just simulated. Right now, what I'm going to do is on top of this, I'm going to plot on top of this histogram, I'm going to plot the density of the gamma distribution, right? Okay, so let me show you how to do that. The first thing you need to do is to define a sequence from 280 to 500 in steps of 0.5. It doesn't need to be 0.5, it could be 0.1. Then you type D you compute the density of the gamma at xv with shape equal to 200 and scale equal to 2. Right, and then you do a lines plot, at xv comma y vg with line type equal to 1, and this is what you will get. As you can see, the, excuse me, just give me a sec. I think, as you can see, the density, the one I have plotted, captures the general shape of the histogram as it should, because we generated a random sample from the gamma distribution and plotted and did a histogram of the generated data. And then, yeah, Vincent, I got a question from Vincent. The XM is basically a random sample of size 100 from a gamma distribution with parameters 200 and 2. And then we did a histogram of the random sample. And on top of the histogram, we have plotted the density of the gamma distribution with the same parameters, 200 and 2. So XM is just a name. Yeah, you're right. It's just a name. I mean, I could have called it anything. I mean, we could have called it any other name. So we have plotted on top of the histogram the density of a gamma distribution with the same parameters that we simulated from, that is 200 and 2. And we plotted the density on the same diagram. So as you can see, the density kind of matches up the histogram as it should, right? All right. Now let's also superimpose on top of this histogram the density of a normal distribution, right? With the mean equal to the mean of the simulated data, and the standard deviation equal to the standard deviation of the simulated data. Right now, if I use the lines command one more time, okay, with line type equal to 2, and let's also change the color to say red or something, right? This is what you get. I mean, you see now you have two lines. You have the histogram and you have the curve in black, which is the density of the gamma distribution. And you have the curve in red, which is the density of the normal distribution. The normal distribution is pretty close to the density of the gamma because it gives a good approximation. Yeah, but in general, it will not be the case. They will not be so close to each other in general. But for the parameter values that we chose, namely for the parameter values of 202, that is, shape is 200 and the scale is 2, it appears that the plotted density of the normal and the true density of the gamma are not too far from each other. Okay. Any questions so far, guys? So this is. I hope I did not skip anything, because I hope, did I skip anything? I might have. I think I skipped some. Oh, let me see. Did I? I think, yeah. I don't think I skipped anything here. Let me check. Yeah. So, any questions on the stuff I've done so far, guys? Hello, guys. Talk to me. Are you there? Or just hello, guys. How can we draw two lines in the histogram entirely? I want the upper part is shown too. What do you mean exactly? I don't understand. You mean you want the upper part not to be hidden? Is that what you're saying? Ah, okay, I see what you're saying. All right, so if you want to see the upper part also, then you need to use the violin command. Okay, let me show you how to do it. All right, in that case, let me close this window. All right, let me start again. All right. Okay, I don't know what you mean, but let me answer one question at a time, guys. Give me 1 minute. Okay. Now, if you want to see the whole thing, right? All right, this is the histogram which I just plotted a minute ago. Now, this time I have given the limits for the x-axis and also the limits for the y-axis. So the limits for the x-axis go from 280 to 500, and the limits for the y-axis go from 0 to 0.015. All right, and then I'm going to plot on top of this the density of the gamma distribution, which looks like this, and also the density of the normal, which looks like this. All right, see, now you can see the whole graph, so nothing is hidden here, because I have changed the limits of the x and the y-axis so that you can see everything. You can see everything what is happening. I had another question. How would you do for another that is in gamma? Frequency equal to f means that the y-axis is on the density scale, Vincent. I think I talked about this 2 weeks ago, Vincent. When you say freq equal to f, it means you're plotting the y-axis on the density scale, not the frequency scale. So if you don't put this command, you will have the y-axis in the frequency scale, which you don't want. You want it on the density scale. So you should always put frequency equal to f, especially when you want to compare with continuous or discrete densities. Louisa, I've got another question from Louisa. How would you do this for another distribution that is in gamma? Yeah, you can do it for other distributions. Like, for example, let's suppose, say, I think that's a good question. Okay, let me start all over again, all right? That's a good question. So let me generate a random number from an exponential distribution. I'm sure all of you guys know from probability 1 what an exponential distribution is. Right, so so I'm simulating a random sample of size 100 from an exponential distribution with parameter 2. It has only one parameter, as you know, the exponential, right? And then I'm going to do a histogram of this. So I do use the hist command, so I use the hist command with frequency equal to f, and this is what you get, right? Now, if you look at this, the x-axis goes from 0 to 2.5, all right? So let me specify it. So xlim is 0 to 2.5, okay? All right, now, on top of this, I'm going to plot the density of the exponential distribution. So let me define a sequence from 0 to 2.5, say in steps of 0.01, and then let me define YVG to be the density of the exponential at xv with the rate parameter equal to 2. Then let me use the lines command, which is lines xv YVG with line type equal to 1. And this is what you get. You see, so what I have done here is to simulate data from an exponential and drawn a histogram, and on top of the histogram, I have plotted the true density of the exponential distribution, which is in black, right? Okay, now let me, as I did earlier, let me now also plot the density of the normal, and let's see how it looks like. So this is the density of the normal, right? Then I want to plot this. This is what you get. You see, now they are not close anymore. As I said before, you see, the density of the normal is not a good approximation to the histogram or the true density of the exponential, as you can see. They are not, I mean, they are close in some parts, but they're not close in general. They are not close at all. All right, so this is another example. This is another example of, I hope this makes sense to you, Louisa. So this is, so there are three things here. One is the histogram of the simulated data. Two is the black line, which is the true density of the simulated data, the exponential density. And the curve in red is kind of a normal approximation for the histogram, but it's not a good approximation, as you can see. All right, okay, so now let's go to the exercise part of there are 4 exercises, or 5. There are 5 exercises. So can we start with the first one, please? Can we start with exercise 1? Exercise 1 of the tutorial sheet, right? So this is exercise 1. The first exercise is you've got a binomial distribution. Sorry, you've got a binomial. This x is binomial with parameters 100 and 0.3. That we are given, and the question is to find the first part is to find the probability that x is equal to 33. So to find this, we just use the dbinom command at 33 with size equal to 100, excuse me, and probability equal to 0.3. So that's the answer to the first part. To answer the second part, which is to find the probability that x is between 28 and 34. Now, as I said before, you can write this probability as this, right? Okay, as the difference of the two probabilities. It's 27, not 28, because as you know, it's a discrete distribution. So to compute this, you will use the command pbinom 34 size equal to 100, prob equal to 0.3 minus pbinom 27 size equal to 100, prob equal to 0.3. All right, so this computes. So this is the second part of the question. The third part of the question is to find the probability that x is less than 38, right? Now, x is less than 38 is the same as the probability that x is less than or equal to 37, all right? So what you need to do is you need to 37 size equal to 100, prob equal to 0.3. All right, so that's the third part of the question. Are you guys okay with this or no? All right, so first, are you okay with this? Yeah, good. So that's completes part 1. Part 2 is to use a normal approximation. I'm not sure I did cover this in the class, so I will skip this. I will skip part 2 because I did not cover normal approximation in the class, so I don't expect you to know this. But if you want to know the solution, I will post it later this week on Wednesday, right? So you can see the solution. But I haven't covered normal approximation in the class, right? So let's go to question 2. Question 2, there are 2 parts once again. The first part says you have, so let's go to, this is exercise 2. All right, the first part is asking you, you have a Poisson variable, you have a x has Poisson distribution with parameter 10, right? And the first part is to plot the PMF of the Poisson with parameter 10 over the values 0 to 25. So let's define these numbers 0 to 25 and let y be the density of the Poisson at x with lambda equal to 10, right? Then if you do plot x comma y, this is, so what I have plotted here, is the density of the Poisson distribution, right? Okay, right? And the question is also asking you to figure out the probability that x is less than 15. Now this you can write as the probability that x is less than or equal to 14, right? So this will be p Poisson, right, at 14 with lambda equal to 10, right? And the question is also asking you to find the probability that x is greater than or equal to 8, which is, I'm sure you know this is from probability 1. This is the same as the probability that x is less than 8. 1 minus the probability that x is less than 8, which is 1 minus the probability that x is less than or equal to 7. All right, so if you want to compute this in R, you will say 1 minus P Poisson 7 lambda equal to 10. And finally, the question is asking you to find the probability that x is between 6 and 16, right? Now, this you can write as this. Right? The probability that x between 6 and 16 is the difference of these two probabilities. So this is P Poisson at 16 with lambda equal to 10 minus P Poisson at 5 with lambda equal to 10. Right? So that completes the first part of question 2. Question 3 is asking you to find the lower quartile, median, and the upper quartile. All right, to find the lower quartile, you use the Q Poisson command with 0.25 lambda equal to 10. So this is the lower quartile of the Poisson distribution with lambda equal to 10. This is the median of the Poisson distribution with lambda equal to 10. And this is the upper quartile of the Poisson distribution with lambda equal to 10. So that completes question 2. Are you okay with that? Hello, guys. Any questions so far? Question 2. Hi. You talk to me, guys. Okay, thank you. All right, so let's go to exercise 3. So next one. So is asking you to plot the PDF of X. So here you're told that X is, excuse me, just a minute. Here you're told that X is exponential with parameter 0.2, right? Okay, so now we want to plot it over the range. We want to plot the PDF over the range from 0 to 25. So we need to first define X as a sequence from, say, 0 to 25, say in steps of 1. So you have X as this, right? And then you define Y as the density of the exponential at X with the parameter equal to 0.2, right? Then you say plot X comma Y, and this is what you, so what you have, so what we have plotted here is the density of an exponential distribution with parameter 2. So you can put type equal to L for line. It will look like this, right? Okay. All right. Now, the question is also asking you to find the probability that X is less than 12. Okay. Now, to find this probability, remember for a continuous distribution, less is the same as less than or equal to. Greater than is the same as greater than or equal to. So to find this, all you have to do is just, yeah, that's it. Because the probability X less than 12 is the same as the probability that X is less than or equal to 12, right? The next thing is we want to find this probability, and this can be written as 1 minus the probability that X is less than or equal to 3, right? So to do this in R, you say, right? And the next one is we want to find the probability that X is between 4 and 20. This you can write as the probability that X is less than, or it doesn't matter, less than or less than equal to 20, less than or equal to, minus the probability that X is 4, right? And this you can, in R, you can compute this as, sorry, excuse me. All right, so you're done, all right? So you see, for a continuous case, you don't need to care less about greater than or equal to, or less than or equal to, because they all mean the same. It's only you have to be careful when you deal with the discrete case, like binomial or Poisson, you have to be careful, right? So that's question 3. Okay, is there a second part? Yeah, there is a second part for question 3 is to find the 20th, 50th, and the 80th percentile of the distribution. So to find the 20th percentile, use the Q exponential command with 0.2 and the parameter. So this is the 20th percentile of an exponential distribution. This is the 50th percentile, and this is the 80th percentile. So that completes question number 3. You okay with that, guys? Any question? Any so far on question 3? We just finished question 3. You okay? All right. So let's go to question the exercise. Sorry. What am I saying? Exercise 4. Exercise 4. We have 3 parts to the question. Here, X is normal with parameters mean equal to 20 and variance equal to 7 squared, right? The first part is asking you to plot the density over the region 0 to 40. So let's define X to be the sequence from 0 to 40 in steps of 1, let's say. So, and define Y to be the density of the normal distribution at X with parameter mean equal to 20 and standard deviation equal to 7. Then you plot x versus y. This is what you get. So this is the density, as you can see, it's the density of the normal distribution. You should put type equal to L. This is what you see, right? Okay. The second part is to, sorry, the same part, part one is asking you to find the probability that x is less than 17. Now to do this, you use the command pnorm, right? 17 with mean equal to 20 and standard deviation equal to 2 is equal to 7. So this is the probability that x is less than 17. Again, less than or equal to does not matter, it means the same thing. The next is to find the probability that x is greater than 25. This you can write as 1 minus the probability that x is less than or equal to 25. So this is 1 minus P norm 25 mean equal to 20 and standard deviation equal to 7. Next, we want to find the probability that x is between 13 and 27. Right, this you can write as the difference of these two probabilities. Right, okay, now in R, you can compute this easily like this, mean equal to 20, P norm 13, mean equal to 20, d equal to 7. All right, so this is the answer. All right, so this is part one of question 4. Part 2 is to find the 5th, 10th, 90th, and 95th percentiles. All right, for that, you will use the qnorm command. So to find the 5th percentile, you put 0.05, mean equal to 20, SD equal to 7. So this is the 5th percentile of a normal distribution with mean equal to 20. Standard deviation is 7. To find the 10th percentile, you put 0.1. To find the 90th percentile, you put 0.9. To find the 95th percentile, you put 0.95. Right? And the third part is can you express the percentiles in terms of the percentiles of the standard normal? Yes, it is possible. I don't know whether I taught you this in the class or not, but this is the fact that okay, let me write it down. If I did not teach you, let me tell this again. If x is normal with parameters mu and sigma squared, right, then Q of P, right, of x is equal is the same as mu plus sigma times Q of P of the standard normal distribution. I don't know. Let me pull this window. You can see the whole thing. Did I make this clear now? Right. What I've written here is that if you have a normal variable with mean equal to mu and variance sigma squared, then the Q of P, the quantile function of x, is equal to mu plus sigma times the Q of P of the standard normal random variable. All right. So in order to this is a well-known result. Maybe I did not teach you this, but maybe you know this from probability 1. I don't know. Anyway, the thing is, this result is pretty well known. So you can compute these 4 quantiles using this result also. So for example, to compute the first quantile using this result, let me show you. Okay, what I will remove this because right when I don't put mean or ST, the R automatically assumes that I'm considering the standard normal case where the mean is 0 and the standard deviation is 1. So I multiply this by sigma, which is 7, right? And then you add mu. So it's mu, remember the formula, mu plus sigma times Q of P of N01. So it's mu plus sigma times Q of P of N01. This is same as what I got here, right? Now, if I change this to 0.1, same as what I got here. If I change this to 0.9, it's the same as what I got here, right? And finally, if I change this to 0.95, it's the same as what I got here. So you see, both approaches give you the same answer. That's because this formula here is valid, is a correct formula. That is, for a normal variable, the quantile function of this is the same as mu plus sigma times the quantile function of the standard normal. All right, so that completes question 4, guys. Are you okay? Any questions? I think I ran out of time, guys. I don't have time to do question 5. Question 5 is a data example. I run out of time, sorry about it, but I will post all the solutions for all the 5 questions tomorrow or on Thursday. So you will see from the course website the full solutions to all the questions. All right. All right, so if you have any questions, guys? No question, are you sure? By the way, can I remind you that the quiz 4 is due on Thursday this week? All right, so please, I was disappointed last week. Many of you guys did not submit. Maybe all of you did, but some other guys did not submit quiz 3. So I would like all of you to submit quiz 4 before 10 a.m. on Thursday, 11th of March, right? Okay, guys, so have a great evening, guys. So I will talk to you soon. Any questions, as usual, you can contact me 24/7 by email, Skype, Zoom, or phone. My phone number is, I'm sure all of you know, my phone number is 0161 273 2941. That's my home phone number. All right, have a great evening, guys. I hope you right? Okay. Thank you, Christian. Hello guys, you okay? Starting now. Hello guys, good afternoon or good evening, wherever you are. Good evening. All right. All right, guys. So this is a tutorial session involving R. So let me show you the tutorial sheet if you haven't seen it already. So let's share screen. Let me close this. This is the tutorial sheet is, you go to week 5 and click on the sheet. So this is the tutorial sheet. So I will take you through this tutorial sheet line by line as usual, and also at the end of the tutorial sheet there are five exercises, and I will try to do as many of them as I can. Right? Okay. All right, guys. So let me start. Okay, before I start, let me go to page 1. Let me go to page 1 of this tutorial sheet. It gives you here, there's a table here, which is, R has many distributions implemented in it. Some of them are discrete and the others are continuous distributions, right? Some of the discrete distributions are the binomial, Poisson, and etc. Some of the continuous distributions are the uniform, normal, exponential, etc. Right? So, like for each distribution, there's a abbreviation. Like the abbreviation for binomial is BINOM. The abbreviation for Poisson is POIS. The abbreviation for geometric is GEOM. The abbreviation for uniform is UNIF. For normal, it is NORM, and so on. Right? Now, for every distribution, the R can compute the density, the probabilities of the CDF, the quantiles, and the random numbers. So these are the four. The DPQR is a common thing in R. So it is used to compute. So for example, DName, if you put the name of the distribution, it will compute the density. So it could be, for example, DNorm, or right. PName will compute the CDF or the probabilities. QName will compute the quantiles of the distribution. RName will compute the random numbers of the distribution. So, for example, if you use norm, remember norm is norm is the abbreviation for the normal, right? So dnorm will compute the density of the normal, pnorm will compute the CDF of the normal, qnorm will compute the quantile function of the normal, and rnorm will compute the random numbers from normal, right? All right, so I just want you to know this right before I go to the next page, right? All right. Now, the first thing I want to do is to open R. So I go to Start button. All right, so this is what you get, okay? The first thing I want to just illustrate, starting with the binomial. Remember, binomial is one of the discrete distributions. So let me show you how to plot the density of the PMF of the binomial distribution, right? So first of all, I define X as a sequence from 0 to 50 in steps of 1. And I'm going to compute the density of the binomial at X. Remember, binomial has two parameters. Let me take them to be 50 and, size equal to 50 and prob equal to 0.6, right? And if you now plot it, this is what you will get. So what you have here, guys, is the probability mass function of the binomial with parameters, size parameter 50 and probability parameter 0.6, right? By the way, can you see the R, what I'm typing or not? Okay, all right, thank you guys. I just wanted to check. I had some problem in the last session. Okay, thank you. So you see what I have plotted is the PMF, or the probability mass function of the binomial with parameters 50 and 0.6, right? Now suppose if you want, you can use the type equal to L for line to join the points up. So you will get something like this, right? Now suppose you want to compute the density of the binomial at 35, right? So I'm assuming here x is binomial with parameters 50 and 0.6. Yeah. Now suppose I want to find the probability that x is equal to 35. Okay, in order to do this, you use this command here, d binom 35 probability equal to 50 and sorry, size equal to 50. I mean size equal to 50 and probability equal to 0.6. This is what you will get, right? So this command here will compute the probability that x equal to 35, right? Okay, now suppose you want to find the probability that x is less than or equal to 25. So to do this, you will use the p binomial command, the probability of the binomial when is 25. So this command will compute the probability that x is less than or equal to 25. Now suppose you want to find the probability that x is between 20 and 30, right? Now this, remember, binomial is a discrete distribution, so it takes only integer values. This you can write as the difference of these two probabilities. That's because, okay, let me explain. That is L, sir. That should be L, not 1. It should be L. It should be L, not 1, okay? All right, now to find this probability, you remember, because x is discrete, the binomial is discrete, this probability is the same as the difference of these two. All right, so you can write it as, in R, you can write it as 30, 19, okay, like this, right? Okay, now if you want to find the quantile of a binomial distribution. So for example, suppose you want to find the quantile, the median of the binomial distribution with size parameter equal to 50 and the probability parameter equal to 0.6. And this is the median, right? L stands for line, Marius. L means line. Okay, L, let me type here. L means line, it plots line, right? All right, so this command here computes the median of a binomial, right, with these parameters. If you want to compute the first quartile, you say it's 0.25. If you want to compute the third quartile, you say 0.75 and so on, right? All right, now one final thing is that R binom. R binom is a random number command. So it generates, suppose you want to generate 5 random numbers from a binomial distribution with size parameter equal to 50 and the probability parameter equal to 0.6. This is what you get. Every time you type, you get different numbers, of course, because they are random, right? So what you have is a sequence of 5 numbers as IID from a binomial distribution with parameters 50 and 6.6, right? Okay, all right. Next, okay, now so far I talked about the binomial. The next thing I'm going to talk about is the normal. Now remember, normal is a continuous distribution, right? So if you use the command dnorm, what this does is it computes the density of the normal at 0 when the mean is 0 and the standard deviation is 1. So this is, I mean, if you don't specify the mean and the ST parameters, Now, if you say mean equal to 4 and SD equal to 10, this is what you will get. But if you don't specify the mean and the SD, R will assume that mean is equal to 0 and SD is equal to 1, right? But if you do specify, you need to actually specify them, like 4 and 10, for example, right? Now let me show you how to plot the density of a normal distribution, right? So let me say you have a sequence of numbers, say from -26 to 34 in steps of 0.1, and y is the density of the normal at x with mean equal to 4 and SD equal to 10, standard deviation. Then you should plot x versus y. This is what you will get. So what you see here is the density of a normal distribution with mean equal to 4 and standard deviation equal to 10. You can join them up using type equal to L. Remember, this is L, not line, not 1. Okay, don't confuse. L stands for line, okay, L-I-N-E. So L is an abbreviation for line. So if you do this, this is what you will get, right? Okay. All right, so this is just a simple command for plotting the density of a normal distribution, right? Now, if you want to compute the probabilities associated with the normal distribution, suppose you want to find the probability that x is less than or equal to 4. This is what you will get, right? Or suppose you want to find the probability that x is less than or equal to 4, 8, and 12, and this is what you get. So this is there are 3 probabilities here: x less than or equal to 4, the probability x less than or equal to 8, and the probability that x less than or equal to 12, where x is a normal variable with mean 4 and standard deviation 10. You can also use the qnorm command. Qnorm is a quantile command to compute the quantiles of a normal. So if you type this is the quantile at 0.975 for the standard normal distribution, because we haven't specified the mean or SD, which means that mean is taken to be 0 and SD is taken to be 1. And if you do specify them, like here, for example, to be this, right? And if you want the median, it will be this, right? Because remember, the median and the mean for the normal are the same, right? So the median for a normal is must be equal to 4, which is the mean, right? And finally, you can also generate random numbers from a normal distribution using the rnorm command. So suppose you want to generate five random numbers from a normal with mean equal to 4 and standard deviation 10. This is what, sorry, I made a mistake. What did I do? What did I do here? Mean equal to, sorry, I misspelled. It should be mean, not, right? Okay, so these are the 5 random numbers. And every time you type, you get different numbers, right? Because they are random, right? So these are 5 random numbers each from a normal distribution with mean 4 and standard deviation 10. All right, the next thing I'm going to show you is how to draw a histogram and plot the density on top of it. Now, let me generate random numbers from a gamma distribution. I assume that you have done gamma distribution in probability 1 last semester, right? So what I have done here is I'm generating 100 random numbers from a gamma distribution with shape parameter 200 and scale parameter 2, right? All right, now the next thing I'm going to do is I'm going to draw a histogram of this data that I just simulated with frequency equal to false, means the y-axis is going to be in the density scale, and the limits for the x-axis are going to go from, say, 280 to, say, 500. And this is what you will get, right? So what I have drawn is the density of the simulated data that we simulated from a gamma distribution with these two parameters. Now let me increase the number of breaks, say to 15, so you get something nicer. So this is frequency equal to f means for the density, the y-axis is plotted in the density scale. Yeah. F means false, Marius. F for false. That means the y-axis is plotted in the density scale. Not if you put true, T for true, F for false. If you say true, then the y-axis will be in the frequency scale, and you don't want that, because we are going to compare the density, the histogram, with the density of certain distributions in a minute. So for that reason, we should have the y-axis in the density scale, not in the frequency scale. So therefore, we should have frequency equal to false, not true, right? I hope you follow that, sir. Okay, yeah. All right, okay, the next thing I'm gonna do, guys, is I'm gonna plot on top of this histogram the density of the gamma distribution that we simulated from. To do that, let me do this. Excuse me. X sequence from say 280 to 500, say in steps of say 0.1, right? Then Y is the density of the gamma at X with shape parameter equal to 200 and scale parameter equal to 2, right? And then I would say lines X comma Y with line type equal to 1. All right, you see what is happening here. What you see here is that the black line here is the density of the gamma distribution that we use to simulate the data. So as you will expect, it should be a good match for the histogram, because the histogram represents the data that we simulated from. The data was simulated from a gamma distribution with the parameters 200 and 2. And hence, the density must be a close match to the histogram. LT equal to L, sir. LT is not 1. LT is L, sorry, what did I say? LT equal to L, yeah, like this. That's what, line type, that's line type, that's different, sir. That's not the same. LTY, okay, let me write it down. I think your LTY means line type, right? It takes numerical values. 1, 2, 3. So LTY means line type, yeah. It shouldn't be confused with type. Type means L. A type could be L. L stands for line. But LTY is different from type, right? LTY must take numerical values like 1, 2, 3, etc. Right? All right. Now the next thing I'm going to do is on top of this, I also want to plot the density of the normal distribution, right? So let me compute the density of the normal at X with the mean equal to the mean of XM, right? And the standard deviation equal to the standard deviation of XM, right? And then I will say plot X comma Y, line type equal to 2, and let me say color equal to say red. Oh, sorry. I think I messed up. Sorry. Okay, let me redo this again. I think let me quickly redo this. Just a minute. Give me a sec, guys. Okay, there's this. Oh, this. Oh no. This. It should be lines, not plot. It should be lines. Okay, you see now. I think they're kind of indistinguishable. There are actually there are two different curves here. They are almost on top of each other, right? They are almost on top of each other. So there's a curve in black, which is the density of the gamma distribution, and there's a curve in red, which is the density of the normal distribution, and they are pretty close to each other, right? And they are almost on top of each other. You can't see them separately. By the way, x-lim here, x-lim is the range of the x-axis. So it specifies the range of x-axis to go from 280 to 500, right? That's what x-lim means, right? Okay, all right. So I'm just trying to explain this figure here, guys. There's a histogram, and on top of the histogram, there are two curves. There's a curve in black, which is the density of the gamma distribution that we simulated from, right? And there's a curve in red, right, which we cannot see because they are on top of each other. And the curve in red is the density of the normal distribution, right, with parameters mean equal to the mean of the simulated data, SD equal to the SD of the simulated data. And they happen to be almost equal, the density of the gamma and the density of the normal. They happen to be for this particular data set, they happen to be almost the same, but it may not be the same for every data set. It may not be the case for this particular data. It happens that they are on top of each other, but you should do some other, like I will show you in a minute. Okay, let me show you in a sec. Now, instead of simulating from gamma, let's simulate from some other distribution, say the exponential, right? Right. So let's simulate, say, 100, right? 100 random numbers from an exponential distribution with, say, rate parameter equal to, say, 1, right? And let's do a histogram as before. Let's do a histogram of this data. Or before I do that, let me do like a, excuse me. Let me do a histogram of this just to check the range. This is what you see. This is the histogram of the data. And as you can see, the x-axis goes from 0 to 5. So let me take x-lim, the range of the x-axis, to go from 0 to 5, right? And let's take x to be the sequence from 0 to 5 in steps of 0.1, right? And define y to be the density of the exponential at x with the rate parameter equal to 1. All right, now if you do a line plot of x versus y with the line type equal to, say, 1, this is what you will get. Now you see that the histogram and the density of the exponential, they match pretty well, right? But you should do this, right? You should do this. You should also plot on top of this the density of the normal with the mean equal to the mean of the simulated data and the standard deviation equal to the standard deviation of the simulated data, right? And with line type 2 and, say, color equal to, say, red, this is what you get. You see, now the two curves are not the same. Jack, I'm keep getting an error. Why? I don't know, sir. But just follow my comments, Jack. Follow what I'm doing, Jack, for a sec. I will come back to you in a second. You see what I have done here? In this example, the two curves, the one corresponding to the exponential, the one corresponding to the normal, they're not on top of each other, because in the last example, they happen to be on the top because that was for a particular data set. But here, in general, that is not the case. Like here, in this example, I simulated 100 random numbers from an exponential. And I did a histogram of the data, which is this. And on top of the histogram, I plotted the density of the gamma, which is the black line, right? So the black line matches up the histogram pretty well, as it should, right? Then I also plotted on top of the histogram the density of the normal with the mean equal to the mean of the simulated data and standard deviation equal to the standard deviation of the simulated data. And that is the red line here, the red curve. And that is not a good match. It's not a good match to the histogram, right? So in general, that's not in general, the normal distribution cannot approximate every data. But in the first example it did approximate a particular data. But general is not the case, right? That's what I'm trying to say. All right, guys. So, Jack, I really don't know why you're getting this error. I think maybe you could zoom me some, like after this class, I will explain what the problem is. But for me now, it's really difficult to say, Jack, now what the problem is. I think it may be because you use two plot commands. You can use the plot command only once, right? You can use the plot command only once, and afterwards you have to use the line command. So you need to use the line command to plot something on top of the plot command. You know what I'm saying? If you use two plot commands, then it will override the existing plot. So you won't be able to see it. Whereas if you use the line command on top of a plot, then it will superimpose on top of the plot. Okay, all right. Anyway, so that's any questions on the stuff we did so far? Guys, are you okay? Talk to me, guys. Any questions on the stuff I did so far? Because I'm gonna go to the exercise part now. As you can see, there are 5 exercises now I need to do. There are 5 exercises. So I want you to tell me if you're okay with everything. If you're okay with everything I've done so far, please let me know before I start doing the exercises, right? So let me start with exercise 1. Exercise 1, there are 2 parts. The first part is you're assuming that X is a binomial distribution with parameters 100 and 0.3. And we want to find the probability that X equal to 33, right? Now to find this, all you have is very simple. What you do is D binom, right? 33, size parameter is 100, and the probability parameter is 0.3. That's it, right? Okay, the next thing we want to find is the probability that X is between 28 and 34, right? Now to do this, you need to compute the probability that X is less than or equal to 34 minus the probability that X is less than or equal to 27. You see, that's because, remember, binomial is a integer valued random variable. So the probability that X is between 28 and 34 is the difference of these two. right? So this will be P binom, right, at 34 with size equal to 100 and probability equal to 0.3 minus P binom at 27 with size equal to 100 and probability equal to 0.3. Right. Okay, the next part is to find the probability that X is less than 38. Right, this is the same as the probability that X is less than or equal to 37, right? Because X can only take integer values, right? So this is the same as P binom 37, size equal to 100, and probability equal to 0.3. All right, so that completes the first part of question 1. The second part of question 1 is to talks about normal approximation, but I did not cover that in the class, so I will skip that. I will not ask you any question on normal approximation in the test, sorry, in the exam or anything like that, so don't worry. So I will move on to the next exercise, which is exercise 2, right? The first part of exercise 2 is you have a Poisson variable with parameter 10, right? And we are asked to plot the PMF over the range from 0 to 25. So let X be the sequence from 0 to 25 in steps of 1, right? Let Y be the density of the Poisson distribution at X with the rate parameter, the lambda parameter equal to 10, right? Then you should say plot X comma Y. This is what you will get. So this is the density of the Poisson distribution with lambda equal to 10. If you say type equal to L, you will get this, right? All right, then the next part is to find the probability that X is less than 15, right? This, because X is integer valued, this is the same as the probability that X is less than or equal to 14. So for Poisson, it will be P Poisson at 14, lambda equal to 10. All right. The next part is to find the probability that X is greater than or equal to 8. And this is the same as 1 minus the probability that X is less than 8. And this is the same as 1 minus the probability that X is less than or equal to 7. All right. So 1 minus P Poisson at 7, lambda equal to 10. Are you following me, guys? Let me know if you have any questions. Please feel free to use the chat room. All right. The next part is to find the probability that X is between 6 and 16, right? And this can be written as the probability that X is less than or equal to 16 minus the probability that X is less than or equal to 5, right? All right, remember X is integer valued, right? So in R, you will compute this as P Poisson as 16, lambda equal to 10, P Poisson at 5, lambda equal to 10. All right, so that's the answer. And the next part is to find the lower quartile, median, and upper quartile. So to find the lower quartile, you will use the Q Poisson command with the probability 0.25. So this is the lower quartile of the Poisson distribution with lambda 10. And this is the median, right? And this is the upper quartile, right? So that completes exercise 2. Are you okay so far? Come on, guys, talk to me. Are you okay with exercise 2? Yeah? Yes? No? All right, let me move on to exercise 3 now. Exercise 3 is about exponential distribution. The first part is asking you to plot the density over 0 to 25. So define x as the sequence from 0 to 25, say in steps of 0.1. Then you define y as the density of the exponential at x with parameter 0.2, right? Then you plot x comma y, and this is what you will get. So this is the density of the exponential distribution with parameter 0.2. You should type equal to L. You get a solid line looking like this, right? Okay. Okay, the next part is to find the probability that x is less than 12. Okay, to find this probability, remember for a continuous, exponential is a continuous distribution. So the probability that x is less is the same as x is less than or equal to. So less or less than or equal to does not make a difference. And similarly, greater than or equal to does not make a difference. So to find this probability, you say px 12 with parameter 0.2, right? And similarly, to find the probability that x is greater than 3, you can write this as 1 minus the probability that x is less than or equal to 3, right? And this is p like this, right? Okay, and the next part is to find the probability that x is between 4 and, x is between 4 and 20. And this you can write as the probability that x is less than 20 minus the probability that x is less than or equal to 4, right? And this will, in R, this will be px 20 with parameter 0.2 minus px 4 with parameter 0.2. Right? That's part one. That's part one of question 3. Part 2 is asking you to find the 20th, 50th, and the 80th percentiles. All right, so you use the command qexp. To find the 20th, you put 0.2 with parameter 0.2. So this is the 20th percentile, and this is the 50th percentile, and this is the 80th percentile, okay, of a exponential distribution with parameter 0.2. All right, so that completes question 3, guys. Are you okay with this? Come on, talk to me. I'm done. Are you okay with question 3? Okay, let me go to the next question, which is exercise 4. Exercise 4 is about the normal distribution. So we're assuming that x is normal. We're assuming x is normal with parameters, the mean equal to 20 and variance equal to 49 or 7 power 2. The first part is asking you to plot the PDF over the range sequence from 0 to 40, say in steps 0.1. So then you take y to be the density of the normal at x with the mean equal to 20 and the standard deviation equal to 7. So you say plot x comma y is what you get. So what you see here is the density of a normal with mean parameter equal to 20 and the standard deviation parameter equal to 7, right? You can use type equal to L. You can use, you can use type equal to L to have a smooth line like this, right? Okay. Right, the question also asking you to find the probability that x is less than 17. So to find this probability, you just say p norm at 17, mean equal to 20, excuse me, mean equal to 20, standard deviation equal to 7. Right, again, less than or less than or equal to does not matter because normal, as you know, is a continuous distribution. The next is to find the probability that x is greater than 25. And this you can write as one the probability that x is less than or equal to 25. So this is 1 minus the probability of p norm right? So this is what you get, right? All right, next is you want to find the probability that x is between 13 and 27, right? And this you can write as the probability that x is less than 27 minus the probability that x is less than or equal to 13. So in R, you will compute this as p norm at 27, mean equal to 20, standard deviation equal to 7, minus p norm at 13. So is it 13? With mean equal to 20 and standard deviation equal to 7. So this is what you get. All right. Question 3, why not? Just a minute, I've got a question. Why not x less than or equal to 19? I don't understand. You mean in question 3? All right. Question 3 was exponential, right? I mean, exponential is a continuous distribution, sir. So exponential, okay, let me go back to question 3. Exponential is a continuous distribution. So it doesn't matter what you write. I mean, this probability is equal to this. Yeah, you can write it like this. No, it cannot be 19 because x is a continuous. So this is equal to this. I mean, exponential, remember, exponential is not a discrete distribution. So the probability of x between 4 and 20 is the same as the probability that x is less than 20 minus the probability that x is less than or equal to 4, right? Yeah, because it's a continuous distribution, right? Okay, right. Any other questions, guys? Let me know. All right, so this completes part 1 of question 4. Part 2 is to find the percentiles. All right, to find the percentiles, you use the command q norm. So to find the 5th percentile, q norm at 0.05, mean equal to 20, standard deviation equal to 7. So this gives the 5th percentile of a normal with mean equal to 20 and standard deviation 7, right? And this gives the 10th percentile, and this gives the 90th percentile, and this gives the 95th percentile, right? All right, that's how you find the quantiles of a normal distribution with a given mean and a given standard deviation. Part 3 is asking you to take another approach for finding the quantiles of a normal distribution. I don't know if I told you that I don't know if I mentioned this in the class or not, but you might have learned this in probability 1 last semester. If x is normal with parameter mean equal to mu and variance sigma squared, then the quantile function q of p of x, right, is the same as mu plus sigma times the q of p of the standard normal distribution. Do you know this result, guys? you might have seen this before in I don't know which course. That what this says is the following: that if you have a normal variable with mean, mu, and variance sigma squared, then its quantile function q of p is equal to mu plus sigma times the quantile function of the standard normal variable. So this is another way of computing the quantiles of a normal variables. So let me illustrate this. Right now, for this one, we should go to this one here. Right. Instead of doing it like this, you can also say this is mu. Mu is 20 plus sigma, which is 7, times the quantile function of the standard normal, which is 0.05. You don't need to specify the mean or, I mean, remember, if I don't specify the mean or ST, like here, R automatically assumes that the mean is 0 and the ST is 1. And the result that you're getting here is the same as the result that we got earlier here. And similarly, if this is 0.1, the result that you're getting here is the same as this. Similarly, you should put this say 0.9, and this result is the same as this one. And finally, you should put 0.95. This result is the same as this one. Right? So you see that there are two ways of computing the quantiles of a normal distribution. One is to use this qnorm command with the mean and the ST given, whatever they are. Two is to use this formula here. Where mu is the mean that is given to you, sigma is the standard deviation that is given to you, multiplied by the quantile function of the standard normal. Right? That's what I have done here, right? And both approaches should give you the same answer, as you have seen here. They both give the same answer, right? All right, guys. So that's exercise 4. There is one more exercise left, which is exercise 5. But I don't think I have the time for that because I'm nearly running out of time. But before I got to that, I mean, do you have any questions on the stuff I've done so far? On the 4 exercises plus the stuff I did before that? Hello, guys. Talk to me. All is good? All right. Thank you. All right. So I think, I mean, as I run out of time, I don't think I have the time to do question. Did not work for you? No, come on, guys. You should say, you can't just Q naught. You need to specify in brackets the probability that you want. So you should say 20 plus 7 times Q norm of say 0.1. It should work. Did you try? I mean, you should type like this. Of course, this will not work, right? It will not. You can't type like this because you need to specify the probability that you want. Say, for example, 0.5. Yeah, this will work. So try that again, sir. Try that again. You should work, guys. Okay. All right. So what I was saying is that I don't have the time to do exercise 5, but tomorrow, not tomorrow. I mean, on Wednesday, I will post the full solutions to all the exercises in the tutorial sheet on the course website. So you should be able to see the full solutions, the typed solutions, plus the video solutions for all 5 questions in the tutorial sheet on Wednesday. All right. So, but if you want to contact me before that for any other question you have, please feel free to do so. As you know, I am available 24/7. You can Zoom me, you can phone me, Skype me, or email me 24/7. And you know my phone number is My home phone number is 0161 273 2941. Right? All right, guys. So have a great evening. I hope if you have other questions on the stuff I did today, please write. Please use the chat box. I will try to reply as soon as I can. Otherwise, have a great evening and have a good time. I will talk to you. I'll talk to you later, guys. Okay. Thank you. Thank you, guys. And once again, please do not forget to submit the quiz number 4, which is due on Thursday, 10 a.m. UK time, right? So please don't forget. I try to submit before that time, okay?